we present Bayesian fields, task-driven, open set, semantic Gaussian splatting. Consider the task of creating an open set map of objects in this small tabletop scene. This raises three key questions. First, how should we measure whether an observation is relevant for a task? Second, how should semantic observations across multiple views be combined? Third, what is the right granularity to define objects? For the first question, we develop a probabilistic interpretation instead of only using the cosine score between image and text embeddings. For the second, we outperform simple averaging by developing a Bayesian updating strategy. For the third, we use a task-driven framework where the map is at the correct granularity to support tasks a user cares about, using the information bottleneck. For example, given the following set of tasks, Bayesian fields will define the following region of the scene as two objects to support the tasks get mustard and grab ketchup packets. Changing the task list changes Bayesian fields map representation. Here, this region of the scene is now represented as a single object for the task of get condiments for a hamburger. To address the first problem, we confront the issue that the cosine score is typically a narrow range of values and does not give an easily interpretable measure of similarity. Building task-driven maps requires computing how relevant an observation is to a given task. Treating relevance as a binary variable, 0 if irrelevant, or 1 if relevant, we desire the probability of relevance given the cosine score observation. To do this, we collect multiple batches of image and text pairings and compute the pairwise cosine scores between them. We accumulate the positive and negative cosine scores, revealing that they are near-perfect Gaussian distributions. These Gaussians are the probabilities of the cosine score given irrelevance and relevance. From these, we can easily use Bayes' rule to derive the desired probability. To address the second problem of how to combine semantic knowledge across views, we first recognize that there are errors in semantic observations and create a measurement model of semantics by identifying three key areas of potential errors. Firstly, measurements can be affected by viewing angle. To demonstrate, we conduct an experiment where a fixed camera views an expo marker on a turntable and show the cosine score with respect to the task get expo marker. Here we observe a near sinusoidal pattern in cosine score as the marker rotates. Next, we show that measurements are affected by viewing distance. Objects that are too close to the camera or too far away are not observable, creating outlier measurements, as demonstrated in this experiment with a tape measure. Lastly, given a fixed camera and fixed object, we observe approximately Gaussian white noise caused by noise in the foundation model. Armed with this measurement model and probabilistic understanding of semantics, we can apply Bayesian updating to address our second problem of how to combine semantic knowledge across multiple views. We view everything in the scene as having a probability of being relevant to each task. For example, consider our small tabletop scene where we're given the following 7 tasks. We will look at the task, get condiments for a hamburger, as an example. With no observations, everything has an equal probability of being relevant. As we make observations, we update our probabilities using Bayesian updating. The relevant parts of the scene now exhibit higher probabilities of being relevant for the task. Each Gaussian has a vector of probabilities, one for each task. Now that we can fuse observations over time, and to address our last problem of how to form objects at the correct granularity, we use information from image masks to group 3D Gaussians into over-segmented 3D object primitives. These primitives are simply groupings of Gaussians. The scene is now over-segmented into these object primitives. Our final step to address our last problem is to form objects at the correct granularity. For this, we applied the information bottleneck to cluster the object primitives into task-relevant objects at the correct task-driven granularity. The information bottleneck takes in an initial signal, x, which in our case is the 3D object primitives. The goal is to find a compressed signal, x tilde, which in our case is the desired task-relevant objects. This is under the optimization that we want to preserve information between the compressed signal and some variable y that we care about, which in our case is our task list. We compute mutual information from these variables using the probabilities found earlier. We can then incrementally solve the information bottleneck to compress the scene from the 3D object primitives into a final set of task-relevant objects. Any objects that remain in the map that have a low probability to all tasks can be removed. This gives us our final task-relevant representation. We can now extract objects for each task. For example, get condiments for a hamburger, grab off his stapler, find spam. We can do this for many objects in a scene. Changing the task list changes the scene representation. For example, given the task of move hats and gloves, we represent this area of the scene as a pile of hats and gloves. Making the task more specific, such as find beanies and get buckle, results in a different representation at the right granularity. Likewise, this region of the scene can be represented as a pile of office supplies for the task get office supplies, or as components such as a stapler and expo markers. We test Bayesian fields on larger scenes, such as this two-room apartment. Here we show renderings at the poses of the sensor images along with our final output map. We show object extractions for select objects in our map. A large portion of the irrelevant regions of the scene have been clustered into a single magenta-colored object. This demonstrates compression of task-irrelevant parts of the scene. Thanks for watching.